Hey everyone, I'm just here to hopefully make a quick video clarifying on how we find eigenvectors and eigenvalues, because I know the process seems very unintuitive for some people when it's first introduced in their course. I'm going to try and talk through a little bit of the reasoning on how we get there, and hopefully therefore it'll be a bit easier for you to remember when you have to come up with it in an exam or something. So let's just recall the definition of the eigenvector and eigenvalue. Essentially, an eigenvalue is this lambda term, some real number, and these are the eigenvectors, these v's, and the linear map here is A, okay? And this is kind of the equation that we're looking for. We're trying to solve the equation A v bar is equal to lambda v bar for v and lambda, okay? So how do we do this? So let's just quickly change the way we're thinking of this equation. By moving it to the other side, we are solving a v bar minus lambda v bar equal to 0, or equivalently a minus lambda times the identity v bar is equal to 0. Now recall that we're not really ever interested in the solution v bar equals to 0, so let's discount that equation, that solution. Clearly, if v is equal to 0, if we apply a linear map to the 0 vector, we always get out the 0 vector, so we don't care about that one. Because that would be an eigenvector for any real number. For non-zero solutions, if we want a non-zero solution to this equation, we want v to not be 0, then we need to somehow have this thing on the left, this matrix, or rather this linear map. It has to be singular in some way, because in general, if a matrix is invertible, it takes every input to a single output. Now, we don't want this matrix to do that. We want it to send 0 to 0, as well as another vector 0, because we want a solution to this equation. So therefore, we say, if a solution exists, aside from v not equals, aside from v bar equal to 0, exists, so we want a non-zero solution, this thing here has to be non-invertible. A minus lambda times identity must be non-invertible. Okay? And what does that mean? Well, this means the determinant of A minus lambda times the identity should be 0, right? Because if we think about it, a matrix is non-invertible precisely when its determinant is equal to 0. So therefore, recall that this object, depends heavily on lambda. We could choose lambda to be any number, and we'll get out a different thing. So we're looking for the values of lambda. This thing depends on lambda, and we're looking for the values of lambda such that this thing is equal to 0. Therefore, we regard this as a function of lambda. We write this as Ca of lambda, the characteristic polynomial of lambda, because it turns out to be a polynomial in lambdas. Okay? Therefore, and to be clear, when this determinant is equal to 0, this thing is non-invertible, so this thing has many solutions, not just the v equals 0 solution. So therefore, we want Ca of lambda, well, rather, we should, to be a little more precise here, want lambda such that Ca of lambda equals 0, and then AV bar equal to lambda v bar, so that AV bar equals to lambda v bar will have non-zero solutions, which implies that, and if this has non-zero solutions, this implies that lambda is an eigenvalue. Okay? So what that means is that the roots of Ca of lambda are indeed all our eigenvalues. And then once we have our eigenvalues, we can actually just solve immediately for the eigenvectors. I say that. It's honestly often the most cumbersome part. But to solve for v bar then, We can just rearrange this as we did earlier to get it as A minus lambda times the identity applied to V bar is equal to 0. We just need to solve this for V. For V, for each lambda value. So we substitute in each possible lambda value, and then we solve for the eigenvector for that corresponding, eigenvector. So we sub in lambda, and then we solve the equation. Because this will just be a matrix applied to a vector is equal to 0, which we know how to solve. And that'll get us our eigenvectors, and that's why this method works. So the basic idea is we compute the CA of lambda, set it equal to 0 to find its roots. Those roots will be the eigenvalues, and then we just have to go back and solve the system of linear equations. Okay? So hopefully that'll clear things up and make it easier for you to remember how to solve for the eigenvalues and eigenvectors of a matrix.